Nah, oke, selamat bergabung. Terima kasih sudah berpartisipasi pada kuliah tamu untuk hari ini. Semoga dengan mengikuti kuliah tamu ini akan memberikan manfaat. Kita bisa belajar dari pengalaman dan juga ilmu yang akan disampaikan oleh Prof. Zhai. Oke, so selanjutnya saya akan menyampaikan dalam bahasa Inggris ya, supaya semuanya bisa menerima. Oke, good morning, ladies and gentlemen, and also some students. Thank you for your participation in the guest lecture, which will be delivered by Professor Guisheng Zhai from the Department of Mathematical Sciences, Shibaura Institute of Technology, Japan. So first of all, we wanted to say thank you very much to Prof. Zhai for his willingness to give the second guest lecture. So this is the second guest lecture, and the first guest lecture was delivered in the last semester. And the topic of this guest lecture is the continuation of the previous guest lecture. So here we have Pak Basuki. Good morning, Pak Basuki.
Good morning, Pak Diki.
Yeah.
Good morning, Professor Guisheng Zhai. How are you today? Fine.
Professor Widodo, nice to see you again.
Thank you, Pak Diki. Okay.
Yeah. Okay. Thank you very much, Prof. Basuki, for joining the guest lecture.
You are very welcome.
Okay. And we also have Helisha. Good morning, Helisha. How are you? Hello, Helisha. Oh, maybe she's a little bit busy. Maybe she's preparing for something now. Okay, so as an information, so the collaboration between Department of Mathematics ITS and SIT was started for quite some time. I think it was started in 2018 maybe with the World Card Professor and then also the GPPL, which is running for every year. Even in the COVID-19, we still do it in online, and this year we do it offline in Japan. So thank you very much for this mutual collaboration between us. We hope that our collaboration still continues. So in this guest lecture, Prof. Zhai will give maybe talk and also discussion for around 90 minutes or maybe 100 minutes. Maybe there will be also some discussion. So again, thank you very much, Prof. Zhai, for your willingness, and the time is yours. Thank you.
Okay, Dr. Diki. So thank you very much for introduction. I would like to confirm, is my voice okay for you?
Yes, it's clear.
Clear? Okay, so I also would like to thank Professor Basuki Widodo for coming to attend this lecture, and I also saw Professor Mardia now appearing, so thank you so much. And of course, I would like to thank all the participating students to attend this lecture. Well, I thank you all. So, well, shall I share my PowerPoint? Is that okay? No problem?
Yes,
okay.
Yes, that's okay.
Sure. So let me share my PowerPoint. Okay, so as introduced by Dr. Diki, this is a continuation from the last guest lecture. I guess it's in February. Okay, so the topic is about design for Lyapunov stability and stabilization for modern control systems. Let me make it a little larger. Okay, so well, I'm not sure whether how many of you are majored in control or not, but I guess there's a lot of application and theoretical research topic in control. So I would like to share with you some of my my idea and my tool used in my research. Okay, so let me go ahead. Well, so in today's talk, I will first use about 10 minutes to review my previous lecture. Okay, so then I will talk about how to design Lyapunov functions for stability of modern control systems by using a very modern tool, which is called linear matrix inequality. And then, so this is actually, we call it an analysis part. Then I will go to the design part for stabilization. Well, then related to linear matrix inequality, I will talk a little bit about bilinear matrix inequality. And yeah, then I will conclude my talk. So first, I would like to review my talk very quickly. Okay, so in my previous talk, I used several models to talk about the state space representation of modern control systems. Okay, so now you can what we can see a differential equation. Actually, here x of t is a state vector, so it is not scalar; it's a vector usually. And then we have a matrix A here. So A is a kind of system matrix to govern the convergent behavior of the system. And here U of t is a function describing our control input. Okay. So our in control theory, our task is to design U of t so that the behavior of x of t will have some desired performance as we want. Okay, so this is so here. Okay, in this differential equation, the right hand side of the differential equation is a kind of linear function. You know, matrix multiplied by a vector, and u is also a linear term. So this is called a linear control system. And of course, in many applications, we have a much more complicated form, as in this nonlinear system. Okay, so now you can see on the right-hand side, we have a very general nonlinear function f, which is dependent on the state vector and the control input. So, I will give an example for this representation, but I think you can get my idea because for students, for professors in mathematical department, you will have a lot of chance to see this kind of a differential equation, right? So here, okay, again, x of t is the state vector, u of t is the input vector, and y of t is something we can measure from the system, or it may be a vector we would like to design for the real system. Okay, so let me move to the next one. And last time we also talked about, when we talk about stability, we need to define a kind of equilibrium point for the differential equation. So which means, okay, when the state goes stops at some equilibrium point, then it will stay there forever if there's no additional disturbance. Then okay, then we define the stability in the sense of the Lyapunov. Okay, maybe you don't like this kind of definition because we only use mathematical notation to define it. So I think you may want this kind of figure. Okay, by using this kind of figure, okay, when which means if the state starts from a neighborhood around the equilibrium point, then okay, then we will find a little larger area so that the state will not go out of that kind of area, which means, you know, even if the initial state may not be good enough, then the system state will not diverge to infinity, will not go so far from the our desired point. So this is a kind of, you know, very famous concept about stability, or you may call it Lyapunov stability, or stable in the sense of Lyapunov. So this is the first concept. Then for linear systems, we can even we usually discuss a kind of stronger concept, asymptotical stability, which means, okay, so here as shown here, for a small neighborhood of the initial point, we can guarantee the state will converge to zero. So here we suppose zero is the desired equilibrium point. If we have some other desired equilibrium points, then we will use that point on the right side. So okay, the same. We use this figure to say, okay, we start from here. Let me say, okay, pretty good. Okay, let me use maybe I can use some remark here. Not so much. We start from some initial point, then it may go a little far from the initial point, but finally it will go back to our desired point. So now, so compared with the previous Lyapunov stability, here we require the state converge to the equilibrium point. Okay, so now you can see asymptotic stable is a little stronger than Lyapunov stability. And okay, I guess it's okay. Then okay, we have a more strong, I mean, even a much stronger concept, which is called exponential stability. So which means, again, so here, if we can find the state convergence is upper bounded by a kind of exponential function, then we call the system, or the equilibrium point, is exponentially stable. Okay, so now, okay, of course, if this is true, then of course we can obtain this limit, this convergence, right? So now you can see, okay, I think many of you have learned this kind of concept in differential equations. Okay, exponential stability is stronger than asymptotic stability, and then is stronger than the Lyapunov stability. Okay, but actually for linear systems, you know, basically exponential stability is equivalent to asymptotic stability. Okay. Okay, so this is the definition. Then what do we have? Okay, actually last time I used this figure to give you a kind of image about these three stability concept. So suppose we have a surface, and on the right side with there's a friction. On the left side there's no friction. Then okay, you can imagine. Okay, you can imagine what we will have here. So suppose we put a ball here or here. It may stay there temporarily, but if there is a little wind, okay, or there's little disturbance, then of course the ball will, for example, here the balls will go to right side or left side. And then the ball here, of course, will go to left side and will not return to the original position, right? So these two, of course, are not stable positions. And how about this guy? This position, there's no friction. So, well, the ball will stay here from the beginning. But if we give the ball a little force to the left or to the right, then it will go, okay, go left, go right. And because there's no friction, then the ball will have a kind of oscillating behavior around the original position, right? So in this sense, the behavior is not bad because it doesn't go so far from the our desired point, but it will not converge to the original point. So in this sense, we call it Lyapunov stability. And our desired position situation is here. Okay, maybe okay from the beginning we give the ball a little force to right, then we'll go right and the left. But because of the we have a friction here, right? So then the ball will go left, right and left, but the vibrating height will decrease, and finally it will return to the original position and will stay there, right? So this is kind of asymptotic stability here. Okay, so this is the relation between these three Lyapunov function concepts. And now let's go to the next page. And then, okay, so well, now you got the image, and we have also the definition. Then how to use our mathematical knowledge to guarantee the stability of a system. Okay, so then we have the very well-known Lyapunov stability theory. Okay, so Lyapunov stability theory. And well, the basic idea is very clear. Okay, so we use a function. So this function actually it is called. Let me give a little more. It is called a Lyapunov function candidate, and we require this function to be positive definite, which means when x equals 0, it is 0. But for any other non-zero x, v of x must be positive. And then if we can find this function along the trajectory of the differential equation, we'll have this kind of property, which means this positive definite function will not increase for any x. Then of course we can obtain the equilibrium point is stable in the sense of Lyapunov. So here notice we have less than or equal to 0, which means Vx may not converge to zero, but because the derivative of Vx is negative or 0, so then it will never increase, right? So that's the basic idea for Lyapunov theory. Then if we have this stronger requirement instead of this guy, okay, which means for non-zero x, v dot will be is negative, which means Vx will keep decreasing for any non-zero x, right? Then of course, finally, Vx will converge to 0, and then x will also converge to 0. Then we can obtain xe is asymptotically stable. So this is the idea about the Lyapunov stability theory. Okay, I think many of you, maybe all of you are familiar with this kind of stability because we also have the same theory in differential equations, right? Okay, so I think you guys have no problem understanding this key concept. Then okay, so now our problem is how to find this kind of Lyapunov function for a differential equation or for the control system. For example, I remember last time we used this example. Okay, so this this is not so easy, right? Because this is a second order differential equation, and we have we have x2 square, we have x1 x2, and if you are asked to about the convergent behavior of this system, maybe not so difficult, so easy to answer, right? So then, okay, let's try to use this kind of function, and x1 square plus 2x2 square. Of course, this is positive definite function, right? For any non-zero x, it will be positive. It only be zero for at the 0 point. So then, okay, if we compute the derivative of this function along the solution of the differential equation, okay, then we will find, okay, the derivative of this function is always negative for non-zero x. Okay, so now, okay, we can use our Lyapunov stability theory to conclude, okay, V3 will converge to 0, and then because of the positive definite function V3, we can conclude x of t also converge to 0 for whatever initial function, initial value. Is it clear? No trouble, right? So then, okay, well, this is our theory, and then if you use a kind of simulation tool to write down to depict the state behavior, so well, you will find, okay, for any initial point from here converge to 0, from here will also converge to 0, and no, we have no trouble. Okay, so this shows, okay, this kind of function really works for this nonlinear function. Okay, no trouble, right? So okay, so let's go down. Now let's go to the next page. Okay, well, then you may say, oh, for some mathematical differential equation, it may be easy, but for example, given this kind of very simple mechanical system, it's a pendulum here. Okay, we have a pendulum. We have so here we have a ball here, and we have a rope here. So then suppose we want to discuss the behavior of the ball here. Okay, then well, I think there's no difficulty for you guys to obtain this kind of second order differential equation for the angle of the rope here. So this is second order differential equation, and then, well, we have linear terms. We have linear terms, no problem, but we also have non-linear terms here. So well, basically, I mean, it may not be difficult, it may not be easy to know the behavior of this system so easily, right? So then, okay, well, for this kind of system, what do we have? Okay, so as we discussed last time, so in modern control theory, okay, we would like to change this differential equation because this is second order derivative, right? So we use this definition to change this differential equation into a first order differential equation. Now we have two differential equations. So this is actually our nonlinear modern control system model, right? Well, of course, the nonlinear property that doesn't change. We have sine x1 here. Okay, basically this is a nonlinear system. Okay, so then, okay, wait a minute. Okay, if okay, so before using our mathematical theory, we would like to know whether the system is stable or not by using simulation. Then actually, okay, if you use simulation, then you will find Okay, there's something interesting for the behavior of the system. Okay, actually, there are two equilibrium points here. So this is a 0 point, right? 0 point here. Because why 0? Because we have x1 and x2 here, right? This is a second order differential equation. And we also have what? Well, I think you guys know the value of this point here, right? This is 3.14 is pi. So so theta is equal pi and the theta dot equals 0. So we have two equilibrium points. Then, okay, from here, it converges to 0. From here, okay, from here, it is getting close to the second equilibrium point, but it will go away from there and then converge to 0, right? So now you can tell, okay, for this nonlinear system, we know 0, 0. Okay, 0, 0 is stable equilibrium point. And here pi 0 is not, it's an unstable equilibrium point here. Okay, so well, this is what we can observe from our simulation. Then okay, after observing this kind of phenomenon, we can try to use our mathematical knowledge, our control theory, to do something for this system. Okay. So well, let's suppose we would like to check the stability of the 0 point here. Okay. So now let me erase my point here. Then let's go down here. So then actually, okay, well, this is something well known in nonlinear control theory. For this system, we can use a kind of Lyapunov function candidate, which has some physical meaning here. So actually here, the Lyapunov function is composed of potential energy and a kind of kinetic energy here. So then if we use this kind of function and then we compute the derivative of this Lyapunov function, then we will find here. Okay, so the derivative of this Lyapunov function is negative or 0. Okay, it's not positive, which means this kind of function Vx will not converge, will not diverge to infinity. Okay, and of course, because here this is less than or equal to 0, we cannot conclude the 0, 0 equilibrium point is asymptotically stable at once. Because time limitation, I would like to omit the details, but actually we can use some advanced technique to conclude the system is actually asymptotically stable. But well, here I would like to emphasize is okay. So for some physical system, we can use a kind of physical meaning to construct the Lyapunov function, so that we can get the stability or instability for the system. But generally, it is not so easy for many control systems. Okay. So okay. So I think this is what we would like to review for my previous lecture. Is there any question by now? Okay, no trouble. Okay, so if there are no question, I would like to move to our main topic today. So well, maybe you will be a little disappointed. So here, basically for nonlinear system, it is not so easy to construct the Lyapunov function. So here, as I wrote here, basically there's no almighty method for general nonlinear system. But the good news is for linear systems, the answer is yes. We have a lot of good idea, a good tool to to construct the Lyapunov function for linear control systems. Okay, so well, one one idea is here. One idea is, so we would like to consider a kind of quadratic function. So here, x transpose. So T means transpose. X transpose px. So now you can see. Okay, this is a second order function with respect to the states, right? And we use p larger than 0 to denote to say p is symmetric and positive definite, which means, okay, if you're not familiar with this notation, just to recall in linear algebra, okay, so we need okay, I think I have some yeah, he's here. So we need p is symmetric, and p is also basically the eigenvalue of p must be positive. So for this matrix P, we say P is positive definite, and actually it is equivalent. It is equivalent to V of x being positive definite for any non-zero x here. So for linear system, okay, we can let's consider this kind of function. Of course, x is the state vector, so basically we need to consider what kind of p we can use for the system. Okay, so then we find, okay, we know Vx is positive definite. Now another condition for a Lyapunov function is v dot, the derivative of Vx must be what? Must be negative definite, right? So let's compute the derivative. Then we can find, okay, actually the derivative of the function of Vx is described by what? It's also a quadratic function. But now, okay, we have this kind of term related to the original system matrix A. So okay, so recall in our Lyapunov function, we would like the derivative of this function be negative definite, right? So okay, so we need, okay, v dot be negative definite, which means this matrix must be negative definite, which means, okay, this guy must be less than 0 for any non-zero x, right? So okay, so then our condition is reduced to solving p so that A transpose p plus PA being negative definite. Okay, so in modern control, okay, finally we reduced our condition for p is here. Okay, p must be a positive definite matrix, and A transpose p plus PA must be negative definite. Okay, so this is equivalent to the system be asymptotically stable. Okay, is it clear? Okay, no trouble, right? Okay, the basic idea is here. So our question for choosing P now is reduced to solving these two matrix inequality in P, in the matrix P here. Okay, so let me summarize our condition here. Okay, now we can conclude, okay, the design by using the Lyapunov function or matrix inequality by using this conditions. So let me say, okay, the system is asymptotically stable, and because it's linear, so it is also equivalent to exponential stable. If and only if, okay, if and only if what? Actually, for fixed A, we already know this stability is equivalent to what? To the real parts of all of A's eigenvalues are all negative, right? It's very clear. And then, well, if we don't use matrix inequalities, actually, we know this kind of Lyapunov function, the Lyapunov equation for any positive definite Q here. If we can find a positive definite P, so that this is true, then we can also say the system is asymptotic stable. And okay, as I explained right now, actually, this is also equivalent to finding a positive definite P so that this matrix inequality is true. Now we have another one. Okay, this guy is also equivalent to this guy. So well, if I will explain this point a little later about the equivalence between these two matrix inequality. Actually, they are used. They are used in different situations. Both are very important in modern control systems design. So okay, then yeah, as I explained right now, okay, in number 2 we have the so-called Lyapunov equation for Lyapunov stability, and in number 3 and number 4 we have basically matrix inequalities for choosing the Lyapunov function matrix P for stability of the system. Okay, so well, and if you have ever used MATLAB for analysis and design of modern control, I think you know. Okay, for the Lyapunov equation, of course, we can use MATLAB to solve it. And for this kind of matrix inequality, actually, I would like to tell you, they can also be solved efficiently by using MATLAB. So, which means, okay, if given this kind of very simple system, we have a lot of good tools to analyze the system. Okay, we can compute the eigenvalue, we can solve Lyapunov equation, we can solve linear matrix inequalities. A lot of tools. Okay, so that's this is our basic theory for Lyapunov stability of the control systems. Okay, any question by now? No problem. Okay, very interesting, right? Okay, so now let's go ahead. Okay, so well, if some of you are not familiar with matrix inequality, and if you even wonder why we call it a linear matrix inequality, I would like to give you some basic idea about the properties of this kind of matrix inequalities. So here, okay, well, as I explained right now, okay, in linear matrix inequality based control theory, we use a matrix larger than 0 to mean, okay, if you saw this notation here, you need to understand P must be symmetric, and P is also positive definite, which means the eigenvalue of P must be all positive. Okay, and well, of course, we also have negative, right? The same, you know. So if you see a P less than 0, which means a matrix less than 0 means we call it a negative definite, and well, P also must be symmetric. Or in other words, P's eigenvalues are all negative real numbers. Okay, so and if we in addition, if we use P1 larger than P2, okay, which means okay, P1 minus P2 is positive definite. Okay, just as in scalar in scalar real number. Okay, the same is true. Okay. Okay, so this is about the notation here. Now let me erase the remark here. Then okay, actually, if you find, oh, it's very interesting. I would like to check some reference. Then you will find actually LMI, the original LMI formulation actually is defined in scalar variables. Maybe some of you have seen this. So the original formulation or the original algorithm for solving LMI actually starts from this kind of formulation. So here we have a lot of symmetric matrix F0, F1, Fi, Fn, and we have some scalar variables before the symmetric matrix x1, x2, xn. So then if we collect these scalars by using a vector, of course this is a vector. So the original definition for MI actually is this kind of matrix inequality with respect to a lot of scalar variables, right? So then, okay, well, because a lot of variables is in different position. Maybe it's better to collect this kind of variables by using a vector or by using a matrix. Then the matrix may look more compact, more easier to understand. Okay. So we will use our new formulation in the next page instead of this kind of formulation. Before that, I would like to share with you why this kind of LMI formulation is important. Okay, wait a minute. Okay, one reason is this kind of formulation or the problem for the existence of X, this problem is convex. Well, I think most of you, or maybe all of you agree with me. If a problem is convex, then the problem is easier to solve, is easier to analyze in many situations. Okay, so well, I don't know explain why it's convex. It's very easy to check. Okay, for any X, Y satisfying this inequality, then we can also find for any lambda between 0 and 1, lambda X plus 1 minus lambda Y also has the same property. So that's actually the reason for MI being convex. So this is the first reason. MI is convex. Then it is easier to find a good algorithm to solve this kind of a problem. And well, one more reason. Okay, LMI can be simultaneously. We can connect a lot of LMIs, so that we can solve a lot of LMIs simultaneously. Just imagine, if for a linear system, if basically linear system, linear equation, no matter how many variables we have, we can solve it easily, right? Because we can consider a lot of linear equations simultaneously. The same here. We can consider a lot of LMIs simultaneously. So for example, okay, so basically, okay, if we have two LMIs, F1 less than 0, F2 less than 0, then we can use this kind of matrix to denote, to connect them, then okay, we can consider this kind of matrix inequality in our algorithm it can be solved easily. Okay. Well, then, of course, you can even think of a lot of other properties very similar to linear functions to figure out MI is good for finding a solution in analysis and design of control theory. Okay. So because of this kind of properties and some other properties, okay, MI. Now I would like to tell you MI technique is a standard tool in modern control theory, not only in theory but also in application in industry. Many researchers, many engineers, they also use this kind of MIs to do the analysis and design work. Okay, so now let's go ahead. Now I would like to. Okay, so well, as I mentioned right now, okay, in the original formulation there are a lot of scalar variables, but actually in MATLAB toolbox or in control theory, we would like to use a matrix to collect the scalar variables. So let me tell you. Actually, we already mentioned. Okay, this is the condition for Lyapunov stability, right? P is a positive definite, and P transpose P A transpose P plus P must be negative definite. So then, okay, well, this is quite different from the original definition. Is it the same as in the definition? Well, actually, this is the same. Okay, let me explain why it's equivalent to the original formulation. So, for example, if P is a 2x2 matrix, so because P is symmetric, right? So which means, okay, we can suppose P x1 here, because symmetric we have x2 here, and we have x3. So for a 2x2 matrix, we need to determine 3 parameters for the matrix P. Then, okay, I think you can understand this guy. Okay, then we can divide P by using the scalar variable. Okay, can you understand here? Because x1 only appears here, so x1 multiplied by this matrix. X2 appears here, then you know x2 multiplied by this matrix, and x3 multiplied by this guy. So which means P can be divided into 3 terms where we have scalar variables multiplied by some fixed symmetric matrix, right? No problem, right? Then we substitute this P into the original matrix. You will find. Okay, for the first one, this is also a matrix inequality. Okay, P larger than 0, which means, okay, because we want to use less than 0, which means x1 minus e1, x2 minus e2, x3 minus e3 less than 0. This is equivalent to each other, right? And how about this guy? Okay, another one. Okay, we just substitute P into the original one, then we can find x1 multiplied by this guy, x2 multiplied by this guy, and x3 multiplied by this guy, also less than 0. So now actually this is our F1 in the original definition, and F2. Do you agree? X1 F1 plus x2 F2 plus x3 x3 less than 0, right? So now, okay, now you can understand. Now you can understand. Let me erase all the remarks. Now you can understand. This is actually equivalent to the original LMI formulation, right? So that's the reason why why we use this kind of matrix inequality in modern control to describe our result. This is much easier to understand, right? P is here, and okay, the left side P, so we only have P in 2 terms, and we can also tell the left side is linear in the matrix P, right? Okay, so that's the reason why, why we use linear matrix inequality in matrix variable in our theory. Okay. Okay, now let's go ahead. Well, some just for your reference, I think maybe all of you are familiar. Okay, so for definite matrices, we need to recall some properties of it. So definite matrices, okay, for a positive definite, okay, or the eigenvalue. So here lambda is eigenvalue, or eigenvalue or must be positive. Negative definite, the scale, the eigenvalue must be negative. And well, here, if W is a non-singular matrix, then this guy is equivalent to this guy. Remember, we need to multiply from the left by W transpose and from right by W. Okay, and the same is true for negative definite matrices. Okay, and well, because we will use this kind of property to obtain one result later. I would like to recall this property. And one more very important property or lemma in the linear matrix inequalities here. So well, if we have a large matrix, a large inequality here. So here, P1, P2, P3, or both. I mean, are all matrices. So if we would like to obtain this matrix is positive definite, then because the matrix is quite large, then we would like to use some conclusion for smaller size to tell whether this is true or not. Then there is a very good result for this conclusion is here. This fact is equivalent to what? To actually we have two equivalent conclusions for this condition. The first one, if we know P1 is positive definite, then we need another smaller size matrix inequality to tell the original matrix inequality is positive definite. And well, if we don't know clearly P1, instead we know P3. P3 is here. If we know P3 is positive definite, then we can also use another smaller size matrix equality. Both these two, because this is the end, these two must be true. But the good news is, in some case, these two matrix inequalities are of smaller size to conclude the original bigger size matrix inequality. Well, if you have any doubt at this stage about this fact, I suppose I suggest you can check Sure complement on the website to find a lot of result, a lot of explanation about this very famous lemma, and very useful. Okay, so we will use this kind of properties to obtain some good result in our theory. Okay, now let me check my time. Is my time enough? Okay, I think it's okay. So now, okay, well, now we know. Okay, if we use some theory to obtain some condition, then we need to check whether the system is because in MATLAB, LMIs are very easy to solve. But if the matrix inequalities are not linear, then actually it is not easy to solve in MATLAB Toolbox. So we need to tell whether the matrix inequality is linear with respect to variables or not. Of course, variables, although we use matrix to describe variables, but in some case we also need some scalar variables. You know, a scalar is a special case of matrix. It's a one-by-one matrix. It's no problem, right? So, for example, in our previous Lyapunov theory, okay, you know, this is a linear matrix inequality, right? Because on the left side we only have P multiplied by some fixed matrix. They are linear, no trouble. And another guy here, we have X is a variable, so also X multiplied by some constant matrix. So we have no trouble. Both of them are linear matrix inequality. In other words, we call them LMI, linear matrix inequality. And this is also a linear matrix inequality, a linear matrix inequality here. This is a 2x2 matrix, right? Suppose P is a variable, so this is a linear term, and Y is also a variable, but Y multiplied by some constant P linear, and this is also linear. And this is suppose tau is also a scalar variable here, but anyway, tau is multiplied by a constant identity matrix, no trouble. So in this sense, this is also a linear matrix inequality or an LMI. We can use MATLAB to solve this kind of matrix inequality. LMI is very efficiently, no trouble. Okay, so this is some good examples, LMI examples, but let me use some well, not bad examples. Some matrix inequality may not be LMI, but we can try to use some lemma, some property to change the nonlinear matrix inequality into LMIs. Okay, then we can use MATLAB to solve it, right? So for example, okay, this is not linear, because we have what? We have on the left P square. P square is not a linear term, right? So then, okay, by using actually the Shibaura complement in the previous page, this guy is equivalent to this matrix inequality. Now we have linear P, and the constant term P here. No problem, right? And well, if the matrix direction is changed, suppose, okay, so there's a little difference. P squared less than I is also okay. We can use the same, almost the same. But of course, you need to notice the difference between these two matrix inequality. We can also obtain a linear matrix inequality for this kind of nonlinear limitation. And a little more complicated form is here. Okay, actually, we will use this kind of matrix inequality in our robust control theory later. So suppose we have this matrix inequality. We have linear term. We have linear term here, no trouble. We have constant term, no trouble. But we have here, okay, so basically this is similar to P square in this term, P multiplied by P, right? So then this, of course, this is not a linear matrix inequality. It cannot be solved in MATLAB immediately. Then we find that we can use our Shibaura complement to change this matrix inequality into this kind of 2x2 linear matrix inequality here. Now you see, okay, linear term, and PD linear, and D transpose P linear, and the constant, no trouble. Okay, so you know, I would like to emphasize. Okay, so well, in our research, sometimes we cannot obtain linear matrix inequality LMIs from the beginning. In this case, actually, we call this kind of matrix inequality because we have p square, we have p multiplied by p. Basically, we call this kind of matrix inequality bilinear matrix inequality because we have p square, or maybe a p multiplied by some other matrix variable. So that's called in mathematics, we call that kind of term a bilinear term, right? That's the reason why we sometimes we will find, okay, we can only obtain bilinear matrix inequality for the present result, but we need to change the bilinear matrix inequality into linear ones so that we can solve it efficiently in MATLAB. Okay, so I think everything now is ready for us to go to our main result. Well, one more preparation here. So, how to solve linear matrix inequalities in MATLAB? So, well, very easily. I mean, so of course I don't suggest you to copy the source here. You can find this kind of source on the website almost anywhere. You can find. So, for example, in MATLAB, if you want to solve this kind of matrix inequality, there are many different tools. There are many different toolboxes. Here, actually, this is the oldest control toolbox. Actually, when I was a student, the name is LMI toolbox. Several years later, the name of LMI toolbox disappeared, and now we use robust control toolbox in MATLAB to solve this kind of LMIs. Of course, if you are familiar for how to solve this kind of matrix inequality, you can even check YAR MIP. This is also a very well-known toolbox developed several years ago, and it is very efficiently, and it even works for some non-strict matrix inequalities. Here, I just use the oldest one, the very typical one to give you an idea. We define a matrix, we define a variable, and we define what? We define, actually this is we define here. So we define this matrix inequality by using 2 lines. Okay, that's all. Then then we use this kind of command to solve it. Okay, then we got the solution. So P, this is the solution here. So of course you can check P here is positive definite, and P also satisfy the original matrix inequality. Okay. So well, now you know. Okay, MI is good. We can solve it very efficiently in MATLAB. In MATLAB, no problem. Okay. So now, okay, let me use some idea to give you how to use it in our design. Okay, so the first idea I would like to share with you. Okay, in many cases, we also we not only require the state converge to 0, but also we would like to require the state converge to 0 with a specified rate. So here, mu is suppose mu is a positive number to show how fast we would like to require the state to converge. I think you guys know the meaning of e to the power minus mu t, right? if mu is 100, suppose 100, then of course, x of t, the convergence basically, is upper bounded by this differential equation, which means the state will converge just like the exponential function e to the power minus 100t, which is a very fast convergent function, right? Okay, so suppose we would like the system to have this kind of property, then what should we do? Well, in the Lyapunov function, we only require xt converge to 0. We didn't require how fast, how quickly the state converges to 0, right? So now, okay, for this kind of control requirement, what do we do? Well, I think you guys, if I give you the answer, actually, okay, this can be described by using the matrix eigenvalue. If the real part of the eigenvalue is less than minus mu, then we can obtain equivalently the xt convergence will be upper bounded by this kind of exponential function. Do you agree? No problem, right? I think if you recall the state of the differential equation, then I think you can understand what I mean here. So then, okay, actually our control requirement is reduced to this control specification. Then I think you guys know what I mean here. This is what? This is actually equivalent to what? The real parts of the eigenvalues of a plus lambda I less than 0. Do you agree? Right? No problem, right? Then, okay, now this kind of control problem is reduced to, less than 0, the real parts of an eigenvalue, which means we only need to consider the asymptotic stability of a plus mu I instead of I in our previous discussion. Do you agree? Okay, very interesting, right? So now, okay, if you can understand this point, then everything is very easy. Okay, so now, okay, we only need to consider a plus mu I, then okay, if we use the Lyapunov function with the Lyapunov equation a plus mu I multiply p equal minus q. This is our Lyapunov equation. Okay. Then of course, if we use our Lyapunov function inequality, then I think you guys know what I mean here. A plus mu I transpose p plus p multiplied by a plus mu I less than 0. Is that correct? This is our previous linear matrix equality. Then we can actually move, okay. Well, of course, we can use this matrix equality, no problem. If you want to use mu, because mu is a constant value, we can use mu p to the right side here. No problem, right? It's the same. Okay. So now you know. Okay. Our problem is to solve this kind of matrix inequality with respect to positive definite matrix P here. And now I would like to share with you. We can also have the same. We have another similar matrix inequality here, which means what? Ax xa transpose multiplied by 2 mu x, which is also x positive definite. And so these guys are linear matrix inequalities, and the original one is linear, is the Lyapunov equation here. So okay, so in this page, in this page, we described how to use Lyapunov equation, Lyapunov matrix inequality for the design of with convergence rate, as in the title, with convergence rate here. So this is actually, this is actually one important topic in robust control theory. Okay. So this is the first result. Okay, and then I think that's all. Then we have another type of robust
Excuse
stability.
me, Prof. Zhai.
Sure.
Yeah. Could
Go
you about this slide? So I have a question here about the constant mu. Usually, does the constant mu is something that is given constants, or usually the mu is a variable that we would like to find the value?
Oh yeah, very good question. Actually, in my explanation, I would like to mention here, mu is a constant value here. So well, I mean, if it is a good question because because in real problem, we can even consider mu as a variable. Then what kind of question can we have is here. So we can even consider what? Because mu describe the convergence for the state. So then we can even consider what? Consider maximum mu subject to this kind of matrix inequality here. So which means, okay, then we not only have two matrix inequality, but we also have a kind of evaluation function for this problem. Actually, this can also be solved in MATLAB, but maybe for some students this is a little difficult, so then I just omit the details. But as you suggested, we can consider mu as a variable in even when we use MATLAB to solve the problem.
Yeah. Okay. Thank you very much.
Okay. Okay. Thank you for the question.
Yeah.
A very good question. Okay. So now let's go to the next page. Yeah. Now, okay. I would like to talk about another uncertain linear system. So well, actually, here I only use two. There are two fixed matrix, but we only know our system can be described by this kind of convex combination of A1 and A2. We don't know the detail of A. We only know A1, A sub 1, and A sub 2. We don't know lambda. We only know lambda is between 0 and 1. Lambda may be 0.1, maybe 0.9, maybe 0.55. It can change. Then we would like to tell, okay, whether this system is stable or not. Now we have trouble because A is not a constant matrix. It can change. It is not a fixed matrix. Then of course we cannot compute its eigenvalue to tell the asymptotic stability, right? It is not a non-matrix. So then, okay, now the good news is we can use our LMI to give some condition for the stability of this uncertain system, because we don't know A clearly. We only know A is described by the combination of two matrices, and of course this combination can be expanded to the convex combination of a lot of matrices. So now, okay, what can we have here? Actually, I'm sorry. So this is we have a condition for the stability of the system is if we can find the same matrix P here, so that this is true, and this is also true for some positive definite, then we can obtain the system is asymptotic stable. So, well, I mean, you know, if you this is very easy to prove, actually. You know, I think most of you, your guys are good at mathematics and better than me. If you multiply this guy by lambda, and the 1 plus lambda by this guy, and add them together, then you can obtain, the matrix inequality for the original A here. But the key point is here. The key point is the condition. This condition has no relation with lambda, because lambda is unknown. We only know it is only interval from 0 to 1. So this is we have 3 matrices. The first one, second one, third one, but all of them are LMIs. We can solve it very efficiently, no trouble. Then, well, it is also equivalent. If we use X here, I will explain why these guys are true. We will use these guys in our design here. So this is the second result for uncertain linear system. We can use our LMIs to get the good result for the original systems. Okay. So now if there's no question, let me move to the next one. We have another uncertain system. This is also a very typical uncertain system in robust control theory. This is also an uncertain system. But now we only know, the original A. Okay, this is the whole A matrix. But A, we have some known part, but we have some unknown part, dft multiplied by E. So here D and E are known matrices, but f of t is an unknown part. We only know the norm bound is less than 1. It may be 0, it may be 1, it may be 0.5. Because now f of t is a matrix, so this kind of this is a quite typical expression in many control applications, actually. So now, well, I think you can understand. This is even more difficult than the previous case, because this is a time variant function here. We cannot use the eigenvalue of this matrix to tell whether the system is stable or not. Okay, so then what can we do? What can we do by using our matrix inequality? Well, let me tell you some good news. Okay, we can. Okay, first. Okay, this is we consider this is as A. So A transpose P plus PA less than 0. This is true according to our previous result, right? But but now we cannot solve this guy, because we have unknown P here, right? So we would like to delete. We will take out f of t from this matrix inequality, so that we can solve it in our MATLAB, right? Well, so then you may say, oh, how to do that? Well, now I have some good news for you. Okay, so then according to our sure complement. Okay, so from here to here, no, from here to here we used this condition. So then we can change this matrix inequality equivalently to this matrix inequality. Now, okay, now without FTs here, we don't have any FT here. And which means if this guy is true, then the original one is true for any FT satisfying this condition. But well, the good news is okay. This is a matrix inequality without FT. But now, as I showed you before, we have a double P here, P squared here. We need to use our previous lemma. Actually, this is our sure complement. Do you remember our sure complement? We use our complement, sure complement, to change this matrix inequality into this 2 by 2 matrix inequality. Then we have only linear term here. Then we can solve it in our MATLAB without any trouble. Okay, so now, okay, just give you some concept about how to analyze this the stability of this kind of uncertain system. The result is here. Okay, we need to solve P larger than 0 together with this matrix equality. Then if we can find a solution, then we can obtain this uncertain system is asymptotic stable. Okay, very happy, right? We can solve it. So okay. So by now we actually we have a lot of good news, right? Okay, for the convergence, we can use our MI. For this kind of uncertain system, we can use our MI to do it. And for this kind of uncertain system, we can also use our MI to solve the stability of the system. Oh, I don't have much time. I'm sorry. So let me go quickly. So finally, okay. Okay, by now we only talk about the analysis part. The next is very easy if you take a little equation. Is if we want to design our, now we have a control input. We would like to consider our state feedback for this linear system. Then okay, we just so we would like to design K here, right? So then we substitute U into here. Then we have our closed loop system here. Then according to our previous theory, this is our new A, right? So new A transpose P plus PA less than 0. Okay. Oh, and P must be positive definite. Okay, this is a if and only if condition. But this is a good news. The condition is if and only if. It's very good. But now the bad news is here. We have P is a variable, and T is also a variable. So we have P, BK. Because this is a this is a bilinear term. Do you remember? This is a bilinear matrix inequality. Of course, this is not easy. This is and cannot be solved in MATLAB. Okay. So then what do we do? Okay. Now I would like to use another matrix inequality here. So do you remember another matrix inequality here? Do you remember the X here? Yeah, what is here? Yeah. Do you remember this guy? So this we will use this kind of matrix inequality in our design. So let me tell you how it works. Okay, this is our new A. This is our new A, AX, right? AX is here, and XA transpose is here. We also have the same trouble as before. BKX, right? And K and X are variables. Of course, BKX is a nonlinear term, bilinear term. It cannot be solved easily. But the good news is because K is neighbor to X, and X is a non-singular matrix variable. I'm sorry. So then we can define define a new matrix. We can set KX equal M. Then we have AX, and BKX becomes BM. And now linear term, and linear term. It's a linear matrix inequality. Can be solved very, very easily. And then you may say, oh, then no k. How to obtain k? From this guy, we can solve k easily, because k can be explained, can be described by m multiplied by x inverse very easily. So that's the reason why we need this kind of a new matrix inequality for our design issue. Okay, so now you know how to design k, right? Very easily. Okay, so this is a good news. Then and this is for a certain matrix. Now let me tell you. Okay, give you an example. If we have an uncertain system, we only know A is described by two matrices A1 and A2. We also want to design our U. Okay, so then the same problem. And suppose we even have a more and very ambitious design aim for what? For the convergence. Now this is a kind of integrated design for control system. Do you agree? No, uncertain, and we also require a kind of convergence, right? So then what do we do? Okay, very easily. Okay, so we do the same thing. Substitute UT into here. We have the closed loop system, and we need this matrix A have this kind of convergence, right? Then do you remember? We need the eigenvalue of A plus BK. The real parts are less than minus mu. Do you remember? Then actually we can what? We can write this matrix inequality by using what? By using A1 plus BK and A2 plus BK, the convex combination of here, right? Then our problem is what? We can combine our design theory for uncertain system and for convergence. Then we can do the same thing as before. So now the good news is here. Okay, we can use. Do you remember in our previous theory, we have two matrix inequality for this matrix and matrix inequality, right? So the first one, and the second one. We have the same x here, and we have the x as a variable. And because kx is neighbor to each other, then we can do the same thing, kx equal to m. Then we can change this matrix inequality finally into these two linear matrix inequalities. Now we have additional terms. These terms are for the convergence rate. Do you remember? And this two is of course is for the uncertain term. Okay, so now we are very happy we can use our MI to design some convergence for an uncertain system. Okay, the same discussion can be done for another uncertain system with DFT, but we just omitted the details. No problem. Okay. So finally, I would like to. I think it's almost time. I would like to give you an example here, very brief example. We would like to okay, just as our description, we would like to design for this very simple mechanical system, mass damper system, and of course we use this example in my previous lecture. And this system can be described by this modern control system, control model, right? Do you remember? So UT here. Remember UT here is the FT here. And we suppose what? We suppose the mass is constant, the damper coefficient is constant, and we suppose the spring coefficient. We only know the spring coefficient or on the interval from 2 to 3. Suppose we don't know the detailed value here. Okay, then then this is our uncertain system. Then we suppose so by using this matrix maybe MDK, we can write our A's here. So we have an uncertain K here. and any other variables are I mean are constant here. So now we only know k is larger than 2, less than 3. We would like to design this control system, and of course we have some goal. Suppose we would like to design the convergence by setting mu equal 3. If you check the eigenvalue of the original A, you will find the real parts of the original A are larger than 3, minus 1 or minus 2 or minus something. So which means, okay, we set faster convergence compared with the non-controlled case, right? So, okay, so then this is our control specification convergence for any k on this interval, okay? So very simple, right? So then, okay, then we, well, then you know what I mean, right? K can be described by using lambda. This is a combination with 2 and 3, 2 lambda and 3 multiplied by 2 lambda, right? Then A can be described by using the combination of 2 matrices, right? Just as we desired before, you know, minus 2, minus 3 here. Okay. So then now we are very happy. We formulate our control problem by using our previous discussion. A is described by a combination of 2 matrices, and we have this kind of convergence rate. So then we can, of course, we can use our condition designed before. This is first condition. This is the second condition. A1 is here, A1 is here, and the B mu is given here. And of course, if we desire, as questioned by Dr. Dickey, if we want to design larger mu, we can even consider the optimization of maximizing mu subject to these 3 matrices, matrix inequalities. Okay, then I think you guys know what I mean here. Well, this is the MATLAB sources in my computer. Not so long, right? Or maybe it's about 10 lines. So then we can we find it. Of course we can get the solution. The x is here and m is here and the k is here. And well, of course you can try larger mu. You can even optimize mu. No problem. Here, as I showed, mu equal 3, a1, a2, b is here, and we use this is a1 plus mu I and a2 plus mu I, and then we can solve the k here. Okay. So then, okay, let's check a solution here. Well, so we find the result is good. Okay, so the initial value is 1, 0. Okay, this is the state convergence, and the control effort is here. Control effort is control input. This is u here. This is the x1, x2. So x1 here and x2 converge to 0, right? And well, because we required a very quick or large convergence, it starts from a larger value, then finally it converges to 0. No problem, right? Okay, so I think this is almost everything I would like to share with you. Oh, I just used a very good time. Use almost the full time. I'm sorry. So, well, I would like to conclude my talk here. So, in this talk, we reviewed some Lyapunov stability in modern control theory. We define LMIs and reviews properties, and talked about the analysis and also the stabilization. And of course, we have a lot of topic. I'm sorry. In modern control theory, you can find a lot of interesting topics in LMIs and in matrix inequalities. For example, one interesting topic, actually, I myself have been working in this area for more than 20 years. So it's controller design with structure, specification, and limitation. For example, for a very large scale system, we would like to design the controller composed of decentralized controller. And actually, I think we also have an expert there, and many experts in ETS there. So controller structure, controller size, maybe even the strength of controller, or maybe the order of controller. So a lot of different idea about specification, limitation. Even if the original system may be linear, because of the structure and specification, then the system itself is actually non-linear problem. So we need to figure out how to change the problem into MI so that we can solve it in MATLAB. And if you are good at mathematics, then you may be interested in checking now. Okay, so Lyapunov theory can be expanded to Lassalle's invariance principle. Then we can even use a lot of different variation for matrix inequality for our analysis and design. So I think that's enough for my talk. Okay, and I have two references for you guys to refer. Okay, the left is a very well-known book for nonlinear systems, and the right side is for linear matrix inequality. You can find a lot of matrix inequalities in this book. Okay, and I think this is the title and the author of the books. And okay, I think that's all. Terima kasih banyak.
Terima kasih banyak.
Terima kasih banyak.
Thank you very much.
Yeah.
Thank you.
Thank you. Yeah, thank you very much, Prof. Zhai, for the lecture. It was amazing, I think, from the
Is it
start.
interesting for you?
Yes, of course, It's very interesting.
Yeah, of course.
Yeah. Thank you.
Very interesting.
Oh, I saw Professor Widodo there. Finally. Okay, and nice to see you again. Finally, Harry Widodo, all right?
Yes, I am.
Yeah. Okay.
Yeah. So, is it fine if we have some discussion, Prof. Zhai, maybe for a few minutes?
I have enough time. I think I have about 20 minutes. No problem.
Oh, okay. Yeah. Thank you. So, are there any questions from the participants or the audience about the lecture from Prof. Zhai? Maybe.
Yes, I am.
Yeah, please.
Yeah, sure, please.
In the last section, you said that X1 and X2 convergent. Does it mean that the convergent point is equilibrium point? Yeah, that's right. This.
Yeah, equilibrium point. Yeah, 0.
Yeah. Okay. And also, does it mean stable?
Yes, because our let me show you the this is actually the norm of x of t less than a kind of converging exponential function, right? And the mu is a positive one, which means of course this guy converges to 0. So that's which means of course x of t is a vector, which means all elements of in the vector must converge to 0.
And for future time t will be still in the equilibrium point.
I'm sorry.
It means that for the future, for ongoing time t, and the system still on the F conversion point. That's, we call it as stable.
Oh yeah. So well, this is because this is a linear system, and we suppose for a linear system without a constant term, so 0 is the only equilibrium point, we suppose. If actually in tracking control, we may have different, we may want to have different equilibrium point. In that case, okay, let me use here. So in some other case, if we have different idea about the equilibrium points, then we may use a kind of state transformation to design a new system so that this guy converge to 0. So in that case, okay, then xt will converge to that desired equilibrium points. Because now, you know, in our linear system, we only have 0, the equilibrium points. That's the reason why we require the convergence of xt must converge to 0.
Thank
Is
you.
that okay for you? Okay.
Yeah, thank you.
Okay.
Quite enlightening.
Oh, thank you very much.
Ya, thank you. Terima kasih Pak Wirdo atas pertanyaannya. Are there any questions from the participants or the audience?
Pak Diki, excuse me.
Yeah.
Yes,
Silakan,
I have
Pak Diki.
some
Yeah, sure.
questions to Professor Guisheng. Oh, thank you very much, Pak Diki. Yeah.
My pleasure.
Thank you very much, Professor Guisheng Zhai. This is very
Yes.
interesting and very exciting. Yeah.
Thank you.
Your presentations. I think that one is very useful for solving some problems rather than some problems according to the our problems. Yeah. For instance, to solve the problem of magnetohydrodynamics. Yeah. When the problem is uncertain non-linear system. Yes. So this is open me to use this theory, yeah, or use this explanations, yeah. So this is not the questions. I think may I have your presentations slides because that one is very interesting to me.
No problem. No problem. I will send my slide to Dr. Diki later.
Thank you very much, Prof. Guisheng Zhai.
Yeah. No
Maybe,
problem.
I will
of
give you some.
Of course.
Yeah, thank you. Maybe I will give you some.
Yes, actually, okay. Well, just let you. I mean, you know, I think you are interested in nonlinear uncertain system, right? So so actually, yes. There have already some research in this area. You know, for example, you know, for nonlinear system, you know, if we would like to use linear matrix inequality, then of course we need to consider some kind of equilibrium points, and then consider kind of linearized system around. So here, this is an example for the equilibrium point 0, but of course you can use some other equilibrium points to change it into a linear one, and from some initial point to some first to some equilibrium points. Then you can do the linearization again with respect to another equilibrium point, so that we can move from the initial point to our desired point finally. So of course we need to design a kind of trajectory for the nonlinear system. But the key point is, I think we can try to use some linearization for nonlinear uncertain systems. And well, as I wrote here, for uncertain system, we may have you know, bounded one, polytopic one, and even time variance system. There are a lot of variation in this area. We can try to use this the combination of the techniques. Okay. Thank you very much.
Thank you very much, Professor Guisheng Zhai.
Okay. Thank you.
Thank you, Pak Diki.
Thank you. Thank you.
My pleasure.
Thank
you, Prof. Basuki, for the questions, and thank you also, Prof. Zhai, for maybe later sharing the slides.
Sure, sure. My pleasure. No problem.
It will be useful for us because I think I myself, there are many new things to me, and I need some time to digest those material. Yeah.
You don't know it. You don't need it. You are already an expert. No problem. No problem.
Thank you. So, are
It
there?
means that Pak Diki will send us the material.
I don't know your contact, so maybe what we can do is I will maybe let me see. I will share my email, and if you are interested in Prof. Zhai's slides, you can send me an email later. Is it fine? I already write my email in the chat.
I already sent my email in the
Oh, in the okay, in the di daftar diri Pak ya, daftar diri ya.
Yeah.
Yeah, okay. Yeah, if you already send your email in the presence list, then we will send you the slides later.
Thank you. Send me the final itu.
Okay. Yeah. So, are there any questions?
Yeah, I have question, Pak
Ya,
Diki.
silakan Pak Hari.
Yeah, sure,
thank
sure.
you. Thank you for a wonderful presentation, Prof. Yeah, I have a question. I see that there is a condition for system to be analyzed by Lyapunov table. I see there is a condition. So I mean, why must the system be Lipschitz continuous for analyzed by the Lyapunov table?
Okay, so your question is why we consider continuous time system here, right? Is that
No,
a
no,
question?
no. My question is why we have to meet the Lipschitz continuous. Lipschitz continuous. I think I see the condition. The system should be a Lipschitz continuous.
Oh, yeah.
Yeah.
So that's actually for the oh, sorry, I have a beautiful. Very sorry, I have a beautiful phone call. Sorry. So that's actually for the uniqueness of the solution in differential equation. So here, if we are given a nonlinear differential equation x dot equal fx, then we usually suppose f is Lipschitz continuous with x, so that for a given initial condition, then we can have the only solution x of t for all t. Is that okay for you?
Oh, okay. So it is because we need to have a uniqueness condition, right? Oh,
That's
okay.
right.
Okay. Thank you, Prof. Thank you. Terima kasih Pak Diki. Yeah.
Thank you.
Ya, terima kasih Pak Hari atas pertanyaannya. Okay, are there any other questions? We still have maybe around 5 minutes. Yeah, okay. Yeah, I think there are no questions anymore, Prof. Zhai. And again, I would like to say thank you very much to Prof. Zhai. I think this lecture is amazing and interesting because we learn not only from the theoretical point of view, but we also learn about how to use it in practice. And I think that is very useful for us. And in particular, Prof. Zhai also shown how to implement it in a mass spring temper system, and I think it is amazing in that Prof. Zhai also share the material code how to use it. I think it will be beneficial for us to learn about it, and and have some new inspiration, new insight from it. Okay. Thank you, Prof. Zhai, for the talk, and also thank you for all the audience for participating in this talk. So, as
You're
an
welcome.
information,
Thank you very much. Thank you all
yeah.
for attending this lecture.
Yeah.
Thank you. Thank you,
Thank
Dr.
you,
Diki.
thank you, thank you.
Thank you very much, Prof. Zhai. Yeah.
Okay,
Thank you,
thank you.
Prof. Zhai.
Thank you, Professor.
Yeah,
Thank you,
thank
all,
you.
Hope
thank
meet
all the
you.
professors. Thank you.
Thank you very much.
Okay, I will see you next time. Thank you very
Yeah,
much.
see you.
See you.
Okay. Thank you, Dr. Mardia. Thank you. Bye
Thank
bye.
you. You're
Yeah,
welcome.
thank you.
Okay. Okay. Bye bye.
Bye bye.
Terima kasih Pak Diki undangannya.
Ya, ya terima kasih
Ditunggu.
Bapak-bapak, Ibu-ibu, adik-adik,
Tunggu
mahasiswa.
kiriman materialnya.
Ya, nanti nunggu dari proses dulu, setelah itu kita kirim dari data yang ada di daftar, Pak ya. Ya, oke, terima kasih. Mohon
Izin live
izin.
ya Bapak Ibu.
Ya, saya tutup ya. 3, 2, 1.